of human free will, fate, and determinism have bedeviled human thinkers since the beginning of time. Philosophers, theologians, ethicists, and scientists have all weighed in on this subject, much to the bemusement of ordinary people who just know that they have the freedom, if not always to choose their actions, at least to choose their attitudes towards their fate, and who therefore assume both that God gave them that free will and that God also has that free will. And then planes fall out of the sky, killing beautiful children. There's not a one of us who doesn't have a habit or an addiction or an area of our life that actually doesn't feel very free. The Apostle Paul complained that he keeps doing things he knows he shouldn't do and not knowing things that he knows he should do, and I don't know about you, but I can relate to that. And then science wades in with its big boots, and the result has been pretty demoralizing so far, actually. The billiard ball universe has no place for free will, human or divine. This seems to be an especially interesting problem for the UU scientists among us, and Richard Sonnenfeld is one of them. He and I had originally imagined this sermon as a double date, but Richard did such a great job of explaining science that, and I've had such a challenging week, that what you're going to get this morning is just Richard. He is a professor of physics at New Mexico Tech and a gifted lecturer. He's been a lay leader of the Socorro Branch of this congregation since its inception. He's also a photographer. By another coincidence, this is his picture on the front of your order of service right now. And of course, he's married to our new DRE, Candy Lindquist. Thanks, Richard, for helping us to understand our world and the intersection of science and spirituality, and hope you got a loud voice today.
Good morning, all. This is a technically intensive sermon, so I want to thank John Roth, who's going to be running the projector, and the whole iMinistry crew, Arnie Gullaroo back in the booth there, and of course Christine for inviting me and helping me with this, and my wife Candy, who's been proofreading and helping me write better for 25 years. This microphone is useless, is that correct? Okay. All right. Well, all right. Please do this in the back. I'm looking at you, sir, with the striped shirt. Do this if you can't hear me. Okay. I can speak up. Ah. Okay. I'll speak louder. Okay. Some of you may recall a wonderful sermon that Christine and former ministerial intern Andrew Millard did regarding what modern physics has to say to UUs. They talked about strings and particle physics and all sorts of wonderful stuff that falls under the broad and beautiful area of quantum mechanics. Physicists have a way of taking English words and giving them different meanings. And so, while in common American English, a mechanic is someone who fixes your car, and thus a quantum mechanic fixes very small cars, to a physicist, mechanics means the study of solid objects in motion and how they respond to forces. In the 20th century, we learned that when particles get very small, or atom size, they get sort of fuzzy, and this is the realm of quantum mechanics. Most people have trouble with quantum mechanics, and actually most physicists have trouble with quantum mechanics. So in this sermon, I will not discuss quantum mechanics anymore. I will instead talk about the older subject called classical mechanics. Now, I see some eyes already beginning to glaze over. What is this, a sermon or a physics lecture? Your concern is understandable. In the past 10 years, I have given 1,000 physics lectures, but this is my very first sermon. So let me explain why this is a sermon and why Christine was brave enough to put me up here. UUs value all points of view, and many of us feel at our most spiritual when we are in nature. Physics used to be called natural philosophy, and what physicists do is try to understand nature at the deepest level. To the extent that I personally feel spiritual or feel awestruck by creation, it is when I've learned something new about how the natural world works. I personally find the subject of classical chaos very beautiful, and so I wanted to share it with you. Also, it bears on free will, which is very important, particularly when one is considering ethics and morality, and which Christine has helped me appreciate even more as we evolved this sermon together. Okay, so back to physics. Classical mechanics. Classical mechanics is the physics started by Isaac Newton. It describes planets, pool balls, pendulums, and clocks. Things we can see, things we can touch, things we can heft. You might think that there's nothing new to say about the subject that Isaac Newton didn't say 400 years ago, but there are new developments. Beginning in the 1960s, Edward Lorenz at MIT was led by his studies in computational meteorology to develop chaos theory. I'd like to talk about chaos theory and what it has to say about free will. I will need to explain first why an extreme interpretation of classical mechanics called the clockwork universe takes away free will, and will then show you how chaos theory gives it back. In fact, I'll show that a grandfather clock, the epitome of predictability in a complex world, can itself become chaotic and unpredictable. So, are you ready to be reduced to an entirely predictable machine? People in the 17th and 18th centuries were very excited by modern physics, which to them was Newton's classical mechanics, and philosophers of the period tried to apply it as broadly as possible. The reason for the excitement is that the theory of gravitation predicts the orbits of planets so accurately that eclipses like the annular one we had last May and transits like that of Venus on June 5th can be predicted hundreds or thousands of years in advance. When two billiard balls hit, the classical mechanics of Newton says exactly where they will go and where they'll be at any time in the future based only on their positions and their speeds in the past. Classical mechanics describes the motion of a pendulum, the thing that makes a grandfather clock tick. So what about us? Are we as predictable as the planets, billiard balls, or a pendulum? Here's what the mathematician Pierre-Simon Laplace, inspired by Newton, said about the subject in his philosophical essay on probabilities. He said, "We may regard the present state of the universe as the effect of the past and the cause of the future. An intellect which at any given moment knew all of the forces that animate nature and the mutual positions of the beings that compose it, if this intellect were vast enough to submit the data to analysis, it could condense into a single formula the movement of the greatest bodies of the universe and the smallest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes." So there you go. Laplace would reduce not just you, but the entire universe to a single formula. As a way to make Laplace's dream, or nightmare, even more real, I should point out that modern computers are leading us toward this vast intellect that Laplace suggested was needed to predict the future. We're ready to go to the next slide. So from here on out, I'm going to talk about a pendulum on a grandfather clock. The grandfather clock has a spring which pushes the pendulum at regular intervals, and the spring and the pendulum both operate according to Newton's physics. I'm going to simulate the pendulum of the grandfather clock, and to make it more real that we're talking about free will, when the pendulum stops after 15 seconds of simulation, if it's on the left, you are going to have vanilla ice cream. If it's on the right, you'll have chocolate. We know the initial state of the pendulum, and in this case, the pendulum bob is going to start at 0 angle, there it is actually, and 0 speed. And Laplace said that means that physics determines its entire future state, including what kind of ice cream you're going to have. So here we go. Let's see where it stops. So this is a high swinging pendulum. We're going to watch it for 15 seconds and see where it ends up. Ah, vanilla. Next, we're going to look at that same pendulum in something called state space. I'm going to talk about state space a lot, both because it's beautiful and because it allows you to see just how trapped you are in the clockwork universe. But for now, what it means is that on the x-axis is the angle of the pendulum, okay, and on the y-axis is actually the speed of the pendulum. This is just another way of showing that what the animation of the pendulum showed. The pendulum starts at the red dot in the middle at 0 degrees and 0 speed. Then the spring pushes it, making it go faster and faster until it gets to the lime green, lemon-shaped outer curve. Once the pendulum reaches the curve, it will just cycle around and around on it. The right side of the lemon is where the pendulum is all the way to the right and not moving. The left side of the lemon is where the pendulum's all the way to the left and not moving. The top of the lemon is where the pendulum's back in the middle but moving right, and the bottom of that lemon actually means that the pendulum's in the middle but moving left. So that's how you can read a state space plot. Okay, hopefully you get the picture. The main thing is it's a way of showing what the pendulum is doing at all times, and you don't need an animation to see everything that happens because the colors show the passage of time. So early times are red, turning to orange, turning to yellow, turning to green. Okay? Now I'm going to show you an animation of the pendulum moving through state space to help you understand the stationary picture a little bit more. The colors on the animations and the stationary figures aren't the same, but the color changes indicate the passage of time in both cases. I should also note, if the animation's a little jerky, the poor little laptop can't quite keep up with my software, so imagine it being smooth. Okay, so here is a state space animation of a pendulum that begins at rest and is driven by the spring of a grandfather clock. Okay. So you see also that the shape doesn't appear to change, but actually the color changed. Could we go back a slide and just show it one more time? So you'll see it starts in the middle. It's actually the same thing. Okay, go ahead. It starts in the middle, and then it settles on that lemony thing, which changes color. So time is passing, but what the pendulum's doing isn't changing anymore. And so that lemony shape is called an attractor. And it's called that because the pendulum always ends up there no matter where it starts. Also, at the end of the 15 seconds, now, not only is this pendulum absolutely predictable, it doesn't matter where you started. So I've got 2 slides now, and the first is that first pendulum that started in the middle, and the second is another pendulum that starts at 60 degrees, so the red dot is to the right, meaning you probably kind of wanted chocolate, okay? All right, but at the end of 15 seconds, both of them end up on this lemony attractor, and that little blue box is where the end of 15 seconds is, and you end up with vanilla ice cream in both cases, okay? There is a name for this feeling that you'll always end up with vanilla. So, how's that free will going? Clearly not well for the pendulum. So I'll let you stare at that fate slide, and I'm going to twist the knife some more by explaining how this really does apply to you, and not just to pendula and clocks. The concept of state space can be generalized. If you had 2 pendula, you could show them as a single point moving on 4 axes. The angle of the first pendulum, the angle of the second pendulum, the speed of the first, and the speed of the second. So you can represent two pendula as a point moving on four axes. You would see that the two pendula make a hyperlemon shape in four-dimensional space. Now, I know you can't see four dimensions, and I really don't know what a hyperlemon looks like. But to a mathematician, four dimensions just mean four coordinates: x, y, z, some other letter, maybe q, and the two pendula make a predictable shape, an attractor, in these four coordinates. No matter where you started them, they will always end up on their attractors. And we can extrapolate this idea, okay? This is where it gets real. We can extrapolate this idea and model every electron and atom in your body as a fancy pendulum. They're not driven by springs, but are moved by electrical forces which are just as predictable as springs and gravity. Each of the electron orbits would show up as an attractor in state space. And rather than have the 10 to the 27th power of atoms, roughly, that make up your body, you would have a single point moving in 6 times 10 to the 27th dimensions. Now, we can't see 4 dimensions. We can't see 6 times 10 to the 27th dimensions, but we can imagine them, okay? If your thoughts and feelings are really just encoded in the positions of your atoms, then that single point moving in 6 times 10 to the 27th power dimensions explains your entire state. Not just whether you're sitting or standing or moving, but how you're feeling and what kind of ice cream you are going to have. Mathematically, it's the same to have one dot in 6 times 10 to the 27th dimensions as to have 10 to the 27th particles existing and moving in 3 dimensions. According to Laplace, your entire state, everything about you that's important to know, may be represented as a single dot, tracing a predictable path in a vast space. And just as the pendulum does not fill up its little box on the picture, most of that picture is white, the 10 to the 27th that your dot moves in is unimaginably empty. The path of the dot represents all the actions you take, all the thoughts you think, all the memories you have. The vast space around the dot is the set of infinite possible roads not taken, to quote Robert Frost. The beauty of the state space representation is that if we could show you the shape that the dot makes in all these dimensions, you would be looking at your entire life. Time is already built in. Your dot just drives down the road. Life is a surprise to you, but a creature looking at your life sculpture would seem omniscient because they would know what lay ahead for you. Given enough paper or a way to display all those dimensions, your specific rut, your preordained path through state space could be shown to you, and you would know the future. Depressed? Time for liberation. Let's take the same pendulum on the same grandfather clock, but wind up the spring some more so it pushes the pendulum harder. That's all we're doing. The effect of this is that the pendulum can swing much higher. In fact, when the spring drive is greater than 1, the pendulum can be made to swing over the top, something which is very unclock-like. Here is an animation of a pendulum pushed into chaotic motion. It's already more interesting. Okay, chocolate. Okay, the pendulum started at 0 degrees but didn't seem to have settled on a path. We only let it run for 15 seconds. That path is complicated, but simple physics still predicts that path. The path was generated by a computer program using the same laws of physics that generated the more predictable graphs I showed you. By pushing the pendulum a little harder, I uncovered a nonlinearity in its response that's not noticeable for a more gently swinging pendulum. This nonlinearity is important to chaos. Now, we'll animate the path through state space for the same pendulum. It's a lot more interesting. So it looks like it's going to repeat, but then it does something different. And now it looks like maybe it's going to settle down, but then it comes back in there and starts to go another direction. Okay? And you end up to the right, so that's chocolate. Okay. Okay. Now, I can start that pendulum at 1,000th of a degree instead of 0 degrees. So that pendulum started right in the middle. But I can be 1,000th of a degree off. Now, for the non-chaotic pendulum, I started one at 0 degrees and one at 60 degrees, and you got vanilla ice cream either way. So if I move this one 1,000th of a degree, you wouldn't think it would matter very much. So let's look. So here's state space. For the pendulum, it started at 0 degrees on the top, and the pendulum started at 1,000th of a degree on the bottom. They start out looking similar. That red loop, the red dot's in the same place, the red loop's in the same place, the brown pointy thing is in the same place, the green pointy thing's kind of similar, but the blue thing's completely different. Okay? And you end up with vanilla on the left and chocolate on the right. Okay? And that just ran for 15 seconds. So I only ran that for 15 seconds. Maybe like 15-year-old kids, pendula are wild and crazy, but they'll settle down if you let them run long enough. So we'll run that same pendulum for 100 seconds. Okay, so remember that regular pendulum was stuck on a lemon-shaped attractor. It had a very boring life. The chaotic pendulum seems to be able to go almost anywhere in state space. Now we'll run the simulations for 90 seconds and skip the beginning part so the pictures are not such a mess. Okay, so again, you see one pendulum starts at 0 degrees. We ran it, and actually we're only looking at the last 20 seconds. It ran 90 seconds total. And they don't look anything alike. Chocolate on the right, vanilla on the left. But that second pendulum was only started 1/1,000,000th of a degree different than the first pendulum. You can't see 1/1,000,000th of a degree. That's the same, but the results are completely different. Okay. This is a fundamental attribute of chaos, and it's called sensitive dependence on initial conditions. Popular accounts of chaos call this the butterfly effect. So, what have we learned? We learned that Laplace thought about Newton's work and said we are all completely predictable, like very complicated clocks, and therefore that free will is an illusion. We learned that our actual state could maybe be represented as a single point moving in a vast state space of 6 times 10 to the 27th dimensions, and that if we were complicated clocks, that point would reproduce the same path over and over, even if its period was 1 lifetime. Then we learned that even a single pendulum, one stupid particle from a clock, which is as clockwork as you can get, becomes completely unpredictable as long as you drive it hard enough to bring out the nonlinearities in its equation of motion. It's predictable for a while, maybe 10 or 20 periods, but it diverges exponentially. If you liken the period of a clock to that of an electron orbiting an atom, then the period of an electron orbiting is perhaps a femtosecond, which is 1,000th of a trillionth of a second. So perhaps we are, maybe, theoretically, if we could ever measure that point in state space to begin with, and ignoring quantum mechanics entirely, predictable for femtoseconds. Somehow, I'm not going to lose any sleep over that. Remember I said that one of my joys in life is to understand how the universe works. The first time I worked through all this and saw that the physics of the humble pendulum validated my intuition that I had free will, it was, for me, a spiritual experience. In closing, if even a clock, slightly tweaked, is not predictable beyond several cycles, then I would say that the branch of modern physics, which is called chaos theory, says that you, who are unimaginably more complex than a bob on a string, are absolutely free.